Hello, welcome to Basics of Finite Element Analysis. Today is 8th week, second day of this particular course. In the last lecture, we had discussed some basics of time dependent problems, and also we had provided an overview as to how these time dependent problems are solved. What we will do today is that we will execute the first step of that overall method, and in context of the differential equation which we had explained earlier, we will do a spatial approximation for that particular partial differential equation, and as a consequence of that we would get rid of the partial derivative and change it to change the PD into an ordinary differential equation. So, our theme for today is spatial approximation. And our goal is convert PDE into ODE. Okay. So, we will rewrite that the original differential equation, which was del over del x A del u over del x plus second derivative with respect to x of b del 2 u over del x square, and then I have c naught u plus c 1 del u over del t plus c 2 del 2 u over del t square equals a source term which depends on position and time, and this equation is valid for values of x which lie between L and 0. And then of course, there are boundary conditions and initial conditions which we had listed in the last lecture. For purposes of brevity, I am not going to write them here. So, for spatial approximation, what we do is that we assume a form of u. So, we know that u is dependent on x and time. So, u is the unknown. We know a, b, c naught, c 1, c 2, f in this equation. What we do not know is u, and u is varying with respect to x and time. So, we are trying to figure out what this function is. So, we assume that u is a function of an explicit function of time. So, I will call it uj, and an explicit function of x, and it could be an sum of a lot of these functions. So, here j is equal to 1 to n. So, this particular assumption is fundamentally different from the assumptions which we made when we did not have time dependent problems. There, this term uj was not changing with respect to time. Here, the term uj, which physically would represent displacements of nodes or the values of primary variables at specific nodes, that can fluctuate with time, and that makes sense. So, suppose there is a beam which is vibrating like this, then the nodal displacements of the beam are not fixed in space, they are functions of time. Okay. So, we are assuming that these nodal displacements, at least in context of beam, or nodal primary variables, they are functions of time, and the variation from one node to the other node happens in the same way as we assumed in case of static problems, where time was not a parameter. So, this is an important thing. The second, so this is one thing. The second thing we have assumed here is that the time dependency or time dependence and space dependence they are separated. They are separated. What does that mean? What that means is that there is one function which is phi j, which purely depends on x, and there is another function u j which purely depends on time. So they are mutually separated. So here we have assumed that variables are separable. This is what we have assumed, that variables are separable, and that makes our mathematics easier. Now this variable separable approach, it makes sense if that reflects reality, and in that case things the solutions we get are very accurate. I mean, if I keep on increasing my number of nodes, things become more and more accurate. But in certain problems, these variables may not necessarily be separable. So in those cases, the nodal primary variables may not only be dependent on time, but they may also depend on the positions, especially in nonlinear systems. The position of node may itself change. In a beam, when the beam fluctuates up and down, by and large the position of a particular node, let us say this is a beam and this is one particular node in which we are interested in, the x coordinate of this beam, when it vibrates by a little bit by little amount, the x coordinate does not change much. So its nodal displacement is not a strong function of x, it is primarily a function of time. Okay. But if while it is bending and if it changes significantly, then there could be situations that these nodal primary variables are not only dependent on time, but because their coordinates themselves are shifting. So in that case they are also dependent on x. So in those kind of complex problems which are significantly nonlinear, this variable separable approach may not necessarily work and give us very good results. But even in those situations, it will give us moderately decent results in a large number of circumstances. So in the context of this week of lectures, we are looking at those class of problems where the time dependent part and the space dependent part of the solution can be separated out easily, because that helps us convert this partial differential equation right away into an ordinary differential equation. So this is something extremely important we have to understand, and now what we will do is we will plug this form of solution into the weight into this integral equation and equate it to 0. So what we are going to do is we are going to plug this expression for u into the partial differential equation, calculate the residue, multiply the residue by a weight function, integrate that entire thing over the domain and equate it to 0. So let's say I have an element and its size is he, and I am going to work in local coordinate system. So here my x bar is equal to 0 and here x bar is equal to he. Okay. Couple of other things. Going forward, for purposes of brevity, I may sometimes use del over del x may be written as prime. So if I have del u over del x, then I may express it as u prime. Similarly, if I have del u over del t, then I may express it as u dot. Okay. and specifically I am going to express not x, but del u over del x bar, because my local coordinate system is in terms of a variable x bar. So, we are going to equate the weighted residue to 0. So, this is my weighted residue statement, and the weighted residue statement is 0 to He integral some weight function w, okay. In parenthesis I have minus a u prime, and the entire thing is differentiated with respect to x, plus b u double prime, entire thing differentiated twice with respect to x bar, plus c naught u plus c1 u dot plus c2 u double dot minus f of x and t x bar is equal to 0. So, this is my weighted residue statement, and now what I am going to do is weaken the differentiability conditions on the partial derivatives for x. Okay. So, we are going to develop a weak formulation for this. So, weak formulation, weak form. So, let us say this is equation 1. So, weak form is again integral 0 to He, w will also have to be differentiated. So, w a u prime plus w prime prime b u prime prime plus c 0 u w plus c 1 u dot w plus c 2 u double dot w minus w of x integrated with respect to x bar, and then when some I will get some boundary terms, but before I write those boundary terms, I wanted to explain that when we are weakening the differentiability, we are weakening it only on the x parameter. We are not weakening it on the time parameter. So, we are not, because my w, the weight function, we are assuming that it purely depends on x. Okay. So, we do not shift the differentiability operator to w when in context of time, we only shift it in context of position or x. So, then in addition to this, I have several boundary terms, and those terms are w minus a u prime plus b u prime, the entire thing differentiated once, plus w minus b u prime prime, and these boundary terms I am going to evaluate at locations h and he, and this entire expression is equal to 0. So, this entire expression equals 0. So, I will rewrite this expression 0 to He, and whatever is here, the same thing goes in this bracket. So, this entire expression comes here. So, I am not going to repeat it, but I will now more explicitly state the boundary terms. So, these boundary terms are q1 w evaluated at 0 minus q3 w evaluated at He minus q2 W prime evaluated at 0 minus Q 4 W prime prime evaluated H e, excuse me, this should be only the first derivative, and this entire thing equals 0. So, these are my boundary terms, and these when we do the assembly, then we when we assemble all these element level equations, then the value of these boundary terms essentially comes from our boundary conditions. Okay. So, when we are till so far we do not see the need for initial conditions explicitly, because all what we have done till so far is we have integrated this partial differential equation in space. So, we are getting several boundary terms, and these boundary terms comes from get handled by boundary conditions. When we integrate this equation in time, then we will see that the need for initial condition also comes into picture. So, here Q 1 equals minus A u prime plus B u prime, the entire thing differentiated twice again, and this is evaluated at x is equal to 0. Similarly, Q 3 equals minus of A minus A u prime plus B u prime prime evaluated x is equal to H e. And Q 2 equals minus B u double prime evaluated at x is equal to 0, and Q 4 equals, oh, there should be a plus sign here, and minus B u prime prime evaluated x is equal to H e. So, we have weakened the differentiability operator, and now what we will do is, so this is, let us say this is equation 2, and what we are going to do is we are going to use this form of u, and we will substitute it in equation 2 in this equation. Okay. So, let us do that. So, what we are doing is we are going to replace u of x t with summation of u j, which is a function of time, times phi j, which is a function of x. Okay. So, this is one substitution we will do, and the other thing we will do is we will replace w, which depends only on x, with phi I, which is a function of x. So, I am going to rewrite my equations again. So, for purposes of reference, we are looking at this equation which has lot of terms underlined in red. So, w prime is nothing but phi I prime times A times u prime. So, u prime is summation of u j, and for purposes of brevity, I will not explicitly like u j as a function of time, and then phi j, and j equals 1 to n, and this is differentiated in x, plus b phi I second derivative times u j phi j second derivative plus c naught phi I u j phi j plus C 1 phi I summation of, and here u is differentiated in time. So, when I differentiate this expression in time, I get derivative of uj. So, I get uj dot and then I get phi j plus C2 phi I summation of, and once again the C2 term has second derivative in of u in time. So, I get u j differentiated twice in time times phi j minus w f dx. The whole thing is integrated over not dx, but dx bar. And then of course, I get, and this w is actually phi I. So, it is phi I times f, and this, and then so this entire thing equals. So, I am now shifting all these boundary terms to the right side of equation. So, I get q1 phi 1 evaluated 0 plus q3 phi I. So, sorry, phi I evaluated at He plus q2 phi I prime evaluated at 0 plus q4 phi I prime evaluated at He. So, this is my weak form, and in this weak form I have also included the spatial approximation by, and also in such a way that variables related to time and x are separated. Okay. So, the overall displacement function or u function, primary variable function, has a explicitly time component and explicitly space component, and they are not intermingled. So, this equation I can express it in this form k1 plus k2. So, basically these are three matrices plus m0 times u plus m1 times u dot plus m2 times u double dot is equal to a force function. So, what is m0? So, if I integrate these terms, I get a matrix, and from there I get m0. If I integrate these terms which are associated with velocity variable uj dot, then I get this m1 matrix. And if I integrate terms related to the second derivative of u, then I get m2. And then finally, I have two stiffness matrices. The first stiffness matrix comes from these terms. So, that is k1, and the second stiffness matrix comes from the terms underlined in light blue. So, it is here, and the force term is this entire thing plus the contribution of qi times f. Okay. So, this term has q's and terms due to f, terms due to f. So, this is there. So, explicitly we will write down the relations quickly. K I j 1 equals integral of a phi I phi j dx 0 to h e k I j 2 is equal to 0 to h e b times phi I prime prime phi j prime prime dx. Then m 0 I j equals integral 0 to h e c naught phi I phi j dx bar m 1 I j equals 0 to h e c 1 phi I phi j dx bar and m 2 I j equals 0 to h e c 2 phi I phi j dx bar. Okay. An important thing to note is, okay, so then f I is equal to a Q matrix plus an F matrix. This F matrix is time dependent and also x dependent, and because the solutions of the system change with time, so Q can also change with time. So, Q can also vary with x and time. This is important to note. Finally, in this entire system, we have assumed that A, B, C naught, C1, C2, they can change with x. So, they are also not necessarily position independent, and some of the stiffness terms can not only depend on x because these constants, but they can also vary with time. These terms A, B can change with time. So, K1 and K2 can change with time. So, this is important to note. So, this completes our spatial approximation method, and what we will do tomorrow is, so what we have done is that we have converted the entire partial differential equation into an ordinary differential equation, because now we have nodal displacements in vector u, nodal velocities which are derivatives in time, and nodal accelerations which are second derivatives of time. So, now the differentiability with respect to x is gone. What we are left with now is only differentiability in time. So, now we have reduced that PDE second order partial differential into an ordinary differential equation of second order. So, we will continue this discussion tomorrow and look forward to seeing you tomorrow. Thanks.